All right, so today we're going to be talking about fixing sets of finite groups. These are topics in algebraic graph theory. Our undergraduate team was Umul Ayman, James Zologicina, which is myself, Jason Riley Jr., and Aaron Stales. And we're all undergraduates from the mathematics department at Towson University here in Baltimore, Maryland. So we want to go over a few definitions, theorems, and operations. So we're going to be talking about graph automorphism groups. And the definition reads, an automorphism, which can also be called a symmetry of a graph gamma, is a permutation from the vertex set to the vertex set that preserves the edge set of gamma. And a good way to think about the preservation of the edge set is if two vertices are adjacent, then under any automorphism, they're also going to remain adjacent. The set of all automorphisms of gamma forms a group under function composition called the automorphism group of gamma, denoted by aught gamma. And here we have the classic example of a graph on 4 vertices and 4 edges that has an automorphism group isomorphic to D4. And so we're going to have a rotation by 90, 180, 270, and 360 degrees, where the rotation by 360 degrees is the same as the rotation by 0 degrees. So that's going to act as the group identity. And then we're also going to have reflections, and paired with any of those rotations, that's going to give us the order of the automorphism group, which is going to be 8. So now we're going to talk about fixing numbers and fixing sets. So the fixing number of a graph gamma is the minimum number of vertices that when fixed destroy all non-trivial automorphisms of the graph gamma. Every graph has a fixing number. And it can actually be shown that because the majority of graphs don't actually admit a non-trivial automorphism group, that the majority of graphs actually have fixing number 0. So going back to our example we just showed on the previous slide, say we're to fix that vertex labeled 1. Well, we can see that that reflection across the diagonal that permutes 2 and 4 is still available. And so we need to fix both vertices 1 and 2. Now we want to talk about the fixing set of a finite group G, which has the same notation, but it's going to denote the set of all fixing numbers for all graphs whose automorphism groups are isomorphic to G. And even though they have the same notation, we just want to make that distinction that a fixing set refers to the fixing number for all graphs of some finite group G, and a fixing number refers to some specific graph gamma. Now we want to get into some graph operations that have allowed us to create new graphs from known graphs and to possibly add elements of a fixing set of a finite group. So first, we're going to go over the more familiar line graph operation. And the definition reads, the line graph denoted L of gamma of a graph gamma has the edges of gamma as vertices. 2 vertices of L gamma are adjacent if the edges in gamma to which they correspond have a common vertex. And here on the left, we have an animation of the first to the third line graphs of the star graph on 8 vertices. And we want to note that even though the number of edges and the number of vertices is greatly increasing at each step, it's going to retain the same automorphism group. And it was actually proved by Whitney in the 30s that for a graph with more than 5 vertices, the line graph is actually going to retain that same automorphism group. We also use the inflation operation, which is a little bit less well known than the line graph operation. And the definition reads, the inflation of a graph gamma denoted by inf gamma is a graph with a vertex labeled for each ordered pair V and E, where V and E are a vertex and an edge of gamma, and V and E are incident. The inflation of gamma has an edge between V1 and E1 and V2 and E2 if and only if V1 equals V2 or E1 equals E2. And so just like in the previous example, we use the same star graph on 8 vertices to show the first through the fourth inflations. And a better way to think about the definition is that under the inflation operation, an n-degree vertex is going to become an n-degree complete graph. So in the original graph, we have a vertex of degree 7 right there in the middle. And then we take the inflation of it, it becomes a 7th degree complete graph. And then from there, the number of vertices and the number of edges, it greatly increases. But for our work, we considered only graphs where the inflation operation and the line graph operation retain the same automorphism group.
Now we will examine the fixing sets of the symmetric group S of n. Before we proceed with the fixing sets of these groups, we're gonna continue with the definition. So we know that the symmetric group on n objects S of n is a group of permutations of n objects. It forms a group under function composition, and the order of the group is n factorial. While we were studying the fixing sets of the symmetric group, we came across the following conjecture, which was posed by Gibbons and Lazon, and it states that the fixing sets of the symmetric groups is 1, 2, all the way up to n minus 1. So here's a very helpful table that lists all of the possible elements of the fixing sets of S of n. As a way to read this table, let's solely focus our attention for S9. When we look at the elements of S9, we can see that some of them are encircled with a little square inside, while others just have a square around them. That's because they come from two different graph operations. So for example, the elements 1, 2, 3, and 4 come from studying graphs under inflation, while 6 and 8 with the square around them come from studying graphs under the line graph operation. There are other elements in S9, such as 5 and 7, that don't have anything around them, and that's because they have not yet been identified as being part of the fixing set of S9. This just means that we haven't been able to find any graph that has an automorphism group isomorphic to S9 and has fixing number 5 or 7. Whenever this happens, whenever we are unable to identify a number as being part of the fixing set, we say that there's a gap in the fixing set at these numbers. So for example, there's a gap in the fixing set of S9 at 5, and there's a gap at 7, and so on. One interesting thing to note about the fixing sets of Sn for any of these n, for any n as long as it's greater than or equal to 7, we see that there always tends to be a gap at n minus 2. So for example, S9 has a gap at 7, S10 has a gap at 8, and so forth for n greater than or equal to 7. This theorem above just lists all of the elements that we know for sure will be in the fixing set of S of n, as long as n is greater than or equal to 5. And again, we just found this, we know this from studying those graph operations. So we've been mixing different graph operations on certain graphs to hopefully fill in the gaps that we find in the fixing sets of S of n. But in an effort to hopefully narrow down our search to fill in these gaps, we were able to prove the following theorem that relates the fixing number of a graph to its orbit sizes. The theorem that we proved states as follows. It says that if gamma is a graph such that the automorphism group is isomorphic to Sn for n greater than or equal to 7, and if all orbits of gamma have size less than n choose 2, then the fixing number of gamma will be n minus 1. Note that this not only sort of backs up this pattern that we noticed for having that gap at n minus 2, since we established that these graphs with orbits of size less than n choose 2 will have fixing number n minus 1. It also helps us significantly narrow down our search, because now we can focus our attention to graphs that have orbits of size greater than or equal to n choose 2, and we can try to identify what their fixing number might be. So when we did that, when we focused our attention to graphs that have an orbit size of exactly n choose 2, we proved that in that case, the fixing number of that graph, gamma, will be exactly the floor of 2 times n over 3. So as a way to understand this theorem that we proved, here's an example below. This figure is the line graph of the complete graph on 7 vertices, K7, and this has an automorphism group isomorphic to S7. And this graph is vertex transitive, so it has only one single orbit. It has only one single orbit, and the size of that orbit is exactly 7 choose 2, which is 21. So following this theorem above, the fixing number of this graph should be exactly the floor of 2 times 7 over 3, which is 4. So we've established that the fixing number for graphs with orbits of size 1 or n, and we've established the fixing number for graphs with orbits of size exactly n choose 2. Now we're examining graphs with orbits of size greater than n choose 2, so we can hopefully establish their fixing number or establish some kind of an upper bound on what the fixing number of those graphs might be. We're actually currently working on a proof that states that when the orbit sizes of these graphs are greater than n choose 2, then the fixing number is less than or equal to n minus 3. If we succeed in proving this, not only will we show that there will always be this gap at n minus 2 in the fixing sets of S7, we will also have disproven the conjecture I mentioned earlier that states that the fixing set of S7 is 1, 2, up to n minus 1.
So in addition to the symmetric group, we also explored another group that was called the quasidihedral group, and this can be denoted as QD 2 to the m. So for this group, we are looking at the fixing number of graphs to have an automorphism group isomorphic to the quasidihedral group, and we used a presentation that is shown below with the edge orbits 1x, 1y, and 1xy, and with the edge orbits, we multiply them by every element in the group. And this is going to help us create the vertices and edges to create the graphs. So we use this to create the graphs that are shown below, where the graph on the left has an automorphism group isomorphic to QD16, and the graph on the right has an automorphism group isomorphic to QD32. When we found the fixing number of each of these graphs, we saw that the fixing number was 1. And we took the line graphs and the inflations of these graphs as well, but the fixing number was still 1. So we came up with the conjecture that 1 was the only element in the fixing set. However, we were able to prove this, so we came up with the theorem that the fixing set of QD 2 to the m equals 1. Now that we know what the fixing set is for the quasidihedral group, we wanted to expand our results a little further to look at an open question that was posed by Gibbons and Lazon. And it says, is it true that for all finite non-trivial groups G1 and G2, is the fixing set of G1 plus the fixing set of G2 equal to the fixing set of G1 cross G2, removing the 1? And since we know the fixing set of the quasidihedral group, we wanted to use that as one of these groups to hopefully answer this question. So we started by focusing on QD 2 to the m cross Kn, where Kn is a complete graph on n vertices, and this is for m and n greater than or equal to 4. We're also looking at QD 2 to the m cross Cn for m greater than or equal to 4 and n greater than or equal to 3. And examples of these graphs are shown below, where the graph on the left has an automorphism group isomorphic to QD16 cross K4, and the graph on the right has an automorphism group isomorphic to QD16 cross C5. And we hope to continue to look at different groups to hopefully get an answer to this question in the future.
Additionally, we want to look at other results that we were able to come up with and use throughout our research. So we're going to first look at some things for the symmetric group. So for graph gamma with automorphism group isomorphic to S7, we can show that with an orbit size of 7 choose 2, the fixing number will be less than or equal to 4. And with an orbit size of 7 choose 3, that the fixing number will be less than or equal to 3. Then for a graph gamma with automorphism group isomorphic to Sn, we can show that with an orbit size of exactly n choose 3 or n choose 4, then the fixing number will be less than or equal to n minus 4 or less than or equal to n minus 5 respectively. And with an orbit size exactly np2, then the fixing number will be equal to the ceiling function of n minus 1 over 2. And we also looked at the Johnson graph. This graph will be denoted as J n comma 2, where the vertices are k subsets of integers 1 through n. And first here, we're going to look at this example that will help us show the next result. So we see that for n greater than or equal to 7, the Johnson graph J n comma 2 has fixing number equal to the floor function of 2n over 3. And this example can be seen for J 9 comma 2 with the fixing number 6. And we use these results to help us come up with this next bullet, which is the Johnson graph Jn comma k for k greater than or equal to 2 but less than n over 2, that the fixing number will be equal to the floor function of 2n plus k minus 2 all over k plus 1. And finally, we would like to just acknowledge and thank our faculty mentors, Dr. Lindsay K. Lauderdale and Dr. J. Zimmerman, for their help throughout the semester, as well as Dr. Lauderdale for running the 2021 spring REU and securing the NSA grant, and the NSA for funding our research through their grant. These are a few of our references. Thank you all for listening, and we are open to any questions.